Okay, so this is the progress report for 21st July 2026. Um so the last time we saw a bit of sparse array imaging, and now I've developed the algorithm. Basically like completed the genetic algorithm, which is what we are going to use to get the optimal sparse array. So you can see that if you just use some random sparse array, the loss function, or basically a quantitative metric of how good the imaging quality is going to be, that's going to be not so good. So the loss function is very high, which means the image quality is poor. And you can also see that based on the point spread function. So you see that there's a lot of mass, or basically the acoustic energy outside of the center. So this central part is where we want all the energy to be. So here I'm showing the signed magnitude of the amplitude, and you need to square that to get the actual energy. So the extremely blue and extremely red areas, those are the high energy ones. So in the middle image, you'll see that there's a lot of bright areas even outside of a sort of circle around which so inside of which you should have the highest energy. But then this changes if you optimize. So this is for 16 element subarrays of the transducer elements, and this improves if you have a more optimized subarray, once again of 16 elements. So to the right you see the point spread function of a optimized subarray. Now this obviously does not compare to the full array. So the full array would just be from 0 to 63, all the indices, and that's to the left. So this is just the full matrix capture. And so using the sparse array, you get a sparse matrix capture, which we'll call SMC. Okay. So now you can see the exact image quality from the optimized SMC. So basically whatever subarray we got from the genetic algorithm, which we used to create this PSF, you can see the actual image using that sparse array. So you'll see that there's a lot of this noise around the three main points, and that causes the CNR mainly to degrade really badly. But the other two quantitative metrics, SNR and PSNR, they are pretty high. The MA and RMSE is also sort of high, also sort of good. So in this case it will be lower, right? And this is only with 16 elements, so just 25% of the full width. We are just using 25% of the total array elements. So if you went to 50% sparsity, which is using 32 elements, this would significantly improve. Of course, your frame rate would basically go down by a factor of 4, but then that's a good enough compromise. So I've done it with just 16, but you can also do it with 32, and it's going to end up in much better results. So this is sort of a lower estimate of how good the image quality is going to be. Okay, so what effect does this have on the frame rate? So going from the full matrix capture, which is using n cross n signals, to just a small matrix capture or a sparse matrix capture with some n dash cross n dash signals, the number of patches that have to be sent, they are reduced, and so the frame rate increases by a factor of n by n dash squared. So just to put this in perspective, if you have the same example that I showed you in the last meeting, which is 128 cross 128 grid, the group size of 8 and 64 elements, basically a full matrix capture, you would be getting 30 FPS. But now let's say you dropped it to a sparse matrix capture with just 16 elements. You would be getting an absurdly high frame rate, which is 480 FPS. So this is just times 16, and that's quite a lot of frame rate. So you can go to just 50% sparsity, and then the frame rate would drop down to just 120 FPS, but the image quality would significantly improve. So I'm thinking that this thing is going to be the sweet spot that we want to go in. Okay, now this genetic algorithm takes a lot of time to run, and this is specific to the grid. So every time that you change your configuration, you'll have to rerun the genetic algorithm to get an optimized sparse array. This is somewhat problematic, But thankfully this algorithm is embarrassingly parallel, which means that you can just throw GPUs at it and then it will run in like 2-3 seconds. With just CPU I had to run it for almost one night and some more hours. So more than I think 8 or 9 hours at least. Okay, so the GPU acceleration isn't done yet. There must be some sort of a library which people probably use, but so far I've already done this with very simple sequential CPU NumPy based implementation. Okay, so that's one limitation, that you have to have the grid size, the grid, so whenever you repeat the grid you would have to repeat the whole process, right? That's one limitation. The other limitation is regarding the image quality. So SMC naturally gives a lower image quality. So you can see that in this, right, that the that you see there's a lot of noise farther away from the center point where we were computing the point spread function. Okay, but what's the benefit? It's the frame rate. Now I'm also going to go over some bit of theory on how this exactly happens, what even is the genetic algorithm, and this is going to be very boring math heavy part, so you can just completely ignore it. So just some notation. It's going to be very dense math, I know. So we have subarrays S of size n dash, where n dash is a hyperparameter that we get to choose. It could be 32, for example, that we will consider, and these will always have the indices 0 and n-1. So each subarray will necessarily have the starting and finishing elements in the transducer array. But other than that, the other n-2 elements will be randomly sampled from this set. So basically 1, 2, 3, so on till n-2, because n-1 is already there. Okay, so for a capital S, which is a subarray given by 0 and -1, these two elements added to the sub-subarray. That's a bit of a jargon I'm using there, sub-subarray, very specific to this particular case. But yeah, you take the union of these two, and that gives you the full subarray. Now these sub-subarrays are the ones that we want to solve for. So we want to get the optimal sub-subarray, and the solution space for that is this A set that I have defined, which is basically all A which are subsets of E, such that they have the cardinality of n dash. So pretty simple so far, right? Now let's just define some notation for sampling. So let samp sub k of q represent a freshly sampled subset of cardinality k from the set q. So this is going to be with uniform distribution and no replacement. So using this notation, a randomly picked sub array would be samp n dash minus 2 of E, where E is this 1 till n minus 2 set. So basically you're just choosing n dash minus 2 elements from 1 till n minus 2 without any kind of replacement. Yeah, so not bootstrap, basically just getting a subset, right? Yeah. Okay. Now let's come to some meaty portions. First thing is children and mutation. So this thing is called the genetic algorithm. Why so? It's based on basically how evolution happens in the real world. So let's say you have two parents and they have different genes. When they have a child, what usually happens is that their gene pool is united, and then from that gene pool the child can get any kind of genes that are basically available. So from there it's like some sort of a random selection, right? Now I know it's actually more complicated than that. You have specific genes there, they have different types. There's yeah, I get that, like there's dominant, recessive, and all sorts of weird things going on. So it's not that simple, right? You have multiple genes and this union and then selection thing from that. This is a very simplified way of describing sexual reproduction, but yeah, we're going to go with this. Okay, so the first thing that happens is obviously you have two parents and then they produce a child. Now this child has some of their genes, the union basically, and then it has some genes of its own. So that happens from mutation. So for just the pure gene pool that these two parents have, you can write it as S1 union S2, where S1 S2 are the parents or the sub arrays in our case. You will just sample n dash minus 2 elements from this combined pool P, which is ideally supposed to be S1 union S2. Now there are some edge cases that it can happen that the gene pool is too small or something, and then you have to add more genes. But yeah, in a very simplified fashion, you just take the union and then you sample from that. Now that would be a pure situation where there's no mutation going on, but mutation does happen. So call this function mutate s, which basically just takes one of the elements in this S3, which is the child, and then it replaces that with some other element which is not used inside of S3, right? So formally, basically, it's doing S minus X union Y, where X is in S and Y is not in S, or in particular, it's in E minus S. And these are uniformly and randomly selected from these specific subsets. So S and E minus S. Now, this mutation thing has a, so it's basically with some probability that sometimes you won't have a mutation and sometimes you will have mutation. So say a probability P sub M is the mutation rate. This is a hyperparameter that you have to set for the genetic algorithm. So from any two parents, you can first get the pure child, which is basically child of S1, S2, and then you can mutate that child. And that will give you a more realistic scenario of what the child is actually going to be like. So it's going to be mutate of child of S1, S2. So basically simulating sexual reproduction. Okay. Now that's just like for two parents. What's going to happen overall is that you will have natural selection and then breeding. These are the two processes that will evolve your population to a more fit population. Okay, so before that, let's talk about what fitness even is. So in our specific scenario, we define fitness as the subarrays which produce better quantitative metrics for the point spread function. So from the point spread function, you can get these two metrics, PSL and ISLR. These are defined like this. Yeah, so just some very simple math really. You get these two functions and then you add them. That gives you a custom sort of loss thing. I didn't actually just want to add it. I wanted to have some weightage over there, but it's fine. It doesn't matter. You can just have some sort of custom loss function. And since you're talking about fitness, more is better, so it has to be the negative of the loss. So the higher the function's score is, basically f of s, the higher this quantity is, the more fit an individual is going to be. And in this case, when I say an individual, I mean a sub array. Okay. So now for a population P, which I'm denoting the population by P, which is basically a subset of the whole solution space, one can compute a survivor group using this fitness. So I'm calling the survivor group as NS of P. NS is shorthand for natural selection. I ran out of terminology to use, so I'm just using this. Okay, so you can compute the natural selected population like this. So first you throw away everyone who was not fit. So you have a sort of thresholding. You have a threshold score F, which is a hyperparameter once again. You only take people who are fit, as in their fitness score is higher than F. Then after that is selected, it might sometimes happen that, oh, this is too big of a group, that the population is more than what can naturally be. So let's say that naturally possible population is capped at n. Okay, I don't know why I wrote mod n over here. It's just supposed to be n, but basically the cardinality of P sub s is supposed to be lesser or equal to this n thing. So if it happens to be bigger, we'll just do what nature does, that is, we'll throw away people randomly, right? just out of random chance, people are going to die. Now there's no fitness happening here. Everyone is already fit, and people just unfortunately die, like you got cancer and yeah, something like that. So you just do random sampling from the fit population, and you update this P sub s quantity. So now this P sub s thing is the surviving population. Now what does the surviving population do? It breeds. right? That's what's there on the next slide. But I should tell you this n thing is also hyperparameter, so is this f thing. And I'm not doing any kind of hyperparameter tuning. I've just intuitively set some values, but ideally you should be doing some hyperparameter tuning for genetic algorithm. The thing is, in my case, I was having a bit of computational intensive thing going on because I was using CPU rather than parallelizing this, so it's like the script was taking forever, so I didn't really try anything complicated. No hyperparameter thing, no changing the grid and all. Okay, so now moving on to the other part of this process, which is breeding. So if this part is about just the fitness, this part is about mutation and getting sexual reproduction, producing new offsprings which have different rates than either of the parents individually. So that gives you some sort of a chance to go towards a minima, essentially. So similar to gradient descent, that in the gradient descent case you're just gonna walk towards the local minima. Here as well you are in a sense walking, except the walking is more like a random walk and then people die and stuff like that. So yeah. But right, it's basically a heuristic algorithm, so we don't expect it to be perfect, but yeah. Okay, anyway, so what happens is so you basically get the next generation by first creating children and then mutating them, and then you add this set, or you basically keep creating these new generations till your population size is big enough, right? So we did a survivor thing, right? So our population has been cut by a lot. Now we need to increase that so that it reaches over a threshold. This is a sort of artificial thing going on, because in actuality it does not happen like that. It's a continuous process that people are dying and children are being born continuously, but here we are doing in a two-stage fashion. Now once again, this thing can also be parallelized pretty easily. Okay, so the full algorithm basically is just 2 steps repeating again and again. First you do natural selection and then you do breeding, and you just repeat it c times, where c is some number, and you get a sort of optimum population. Now in that population you just choose the one who is the most fit and go with that. Yeah, right. So about the fitness scores, we are using PSL, which is the maximum side lobe intensity, and this ISLR thing, which is sort of a ratio of the side lobe intensity, the summed side lobe intensity, and the main lobe intensity. Now these main lobe and side lobe are basically regions that you define based on a threshold radius r, which is once again a hyperparameter, so you have to set it on your own. And once you compute these, you can then get the fitness score, right? So just negative of PSL plus ISLR, or whatever custom function you want. And yeah, that's it. That's how you do genetic algorithms. So the main thing that this does is that it optimizes your population, and then since your population is optimized, you can just pick the best individual from that, and then get the best imaging from this. So this imaging thing is just one particular application of the genetic algorithm. This is more general and can be applied anywhere. So this can mainly be used in cases where you don't have the normal strategies that you can rely on, right? So let's say you can't do gradient descent, or you can't do some other thing for optimization. You will have to go with some heuristic based algorithm. So this is the one that I chose to go with. Okay,